Hello. Today we are going to look at Lecture 9, Chapter 14. This is the last lecture within Chapter 14. So this is going to be a pre-lecture review of what's going on so you guys can get an understanding before class. So, Chapter 14, Lecture 9. Okay, so we're going to continue talking about the integrated rate laws. And we're going to start talking about a zero, a zero order reaction. So with a zero order reaction, we have the reaction being independent of any reactant concentration. So remember, m plus n is equal to 0 in this case. Okay. For this, we have a differential rate law. Of A, or delta A over delta T to the negative is equal to K, so it's independent of concentration. Our integrated rate law so if we were to take that differential rate law and find the integral of it, we would get A at time t is equal to negative K T plus A at time 0. So AT, this is the concentration of A at time t. This is our time. K is our rate constant. And A naught or A0 is our initial A concentration. We can then take this and set it up as a equation where y equals mx plus b. In this case, our AT is our y, our slope is negative K, our x is t, and A naught is our y-intercept. Okay, so looking at this, if we take A at time t versus t, we get a linear relationship where the slope is equal to negative K and our y-intercept is A naught. So I'll give you guys a summary of the rate laws within class that summarizes everything for first order, second order, and zero order reactions. But let's go back to our idea of collision theory. So we talked about surface area increasing surface area or surface to volume ratio increases rate, increasing concentration increases rate unless you have zero order, and increasing temperature increases rate. So when we increase concentration, what happens? So as you increase concentration, you're going to increase your collisions because you have a greater number of molecules. So the frequency at which molecules collide is greater. Okay. With our surface area, we just have more surface at which collisions can occur. And then lastly, our increased temperature. With increased temperature, we have a greater number of collisions, and we have a greater number of molecules with the correct amount of energy, or that activation energy, in order for a reaction to occur. So the faster speed of our molecules is because of our kinetic energy equation. And then, as I said, more molecules with the amount of energy required for a reaction to occur. So our EA in this case. Okay. So our integrated rate laws they're going to relate concentration time. How about temperature and our rate? So the equation that relates temperature and the rate constant. Remember, I said that as we increase temperature, we're going to increase our rate constant, and I told you we would eventually look at what relates that, and that is called the Arrhenius equation. Our Arrhenius equation, we would say that its normal form is K is equal to A E negative EA over RT, where K is our rate constant, A is our collision frequency factor, EA is our activation energy, our activation energy itself should be in joules. R is our gas constant, but we want the one that has energy in it, so it is the 8.314 joules over mole times by Kelvin. And then we have our temperature, which is in Kelvin. Make sure you put these units in, or these variables in these units. So, taking our normal form of our equation and we do some math, we get our graphical form, if you will, of this. So our graphical form of the Arrhenius equation is ln K is equal to negative EA over R times by 1 over T plus ln of A. So Our ln of k is our y. Our negative EA over R is our slope. Our 1 over t is our x. And our ln A is going to be our y-intercept. So if we take ln of k versus 1 over t, we get a linear relationship. And in this linear relationship, our slope is equal to negative EA over R, and our y-intercept is equal to ln of A. And this equation should look very similar. It looks like the Clapeyron equation. Okay, we could do some more math, and we can find our 2-point form of the Arrhenius equation. And this is ln k2 over k1 is equal to negative EA over R, 1 over T2 minus 1 over T1. So if you know the rate constant for a specific temperature and the activation energy, you can determine the rate constant at a different temperature, or if you know the rate constant at 2 different temperatures, then you can figure out your activation energy. Okay, moving on from collision theory, we're going to look at what are called reaction mechanisms. Our reaction mechanisms themselves describe the steps of a reaction. These steps, or elementary steps, sum to give us the overall reaction, what we're used to seeing. So some of our elementary steps gives us our overall reaction. And that is the chemical equation that we generally see. So for instance, we have this reaction right here. We have NO gas reacting with another molecule of NO gas to produce N2O2 gas. Okay. Then we take that N2O2 gas and react it with O2 to produce 2NO2 gas. Okay? Overall, we get an equation that looks like this. Which is missing this substance right here. Actually, not sure why I wrote that. It's missing this substance right here. This substance that only appears in elementary steps is called an intermediate. So, as I said, this would be an elementary step. This would be an elementary step. And then this would be the overall reaction, what chemical equation you are used to seeing with no intermediates within there. The intermediates themselves are short-lived and they're made by one reaction, consumed by another. So, with an elementary step, we can use stoichiometry to determine its rate. We do this using something called molecularity. Our molecularity itself basically tells us how many molecules are reacting in a given elementary step. So it uses that, and it uses it to determine the rate law. Okay. So the rate law itself is based on the elementary step that is a slow step within the reaction. And looking at molecularity a little bit more, we can have molecularity that is unimolecular, one molecule, bimolecular, two molecules, or termolecular, three molecules. So something like A to products. So if in elementary steps, if we go from A to products, our rate would be Ka, because this is a unimolecular process. We have something like 2A to products, or A plus B to products, again within an elementary step, and this being our slow elementary step. We'd have rate is equal to Ka squared, or rate is equal to Ka B. So this would be a second order process, right? A unimolecular rate elementary step is a first order process. A bimolecular elementary step is a second order, and then termolecular, which we won't really see, would be a third order. So both of these options are bimolecular, and then there's lots and lots of options for termolecular. I'm only going to give you guys one. So 3 A molecules react to give you products, or if we have A and 2 B's, 2 A's, 2 B's, whatever it happens to be, as long as we have 3 molecules reacting in your elementary step, that would be termolecular, and you'd have a third order process. Okay, so when we have a rate, or when we have a elementary step that is a slow step, we can determine the rate law using that elementary step and based on its number of molecules. Okay, so let me give you some examples. I'm going to work them out in a different video, but for instance, let's take this mechanism. So we've got this initial, elementary step. And we would say that this one is our slow one. And then we have a second elementary step with a different rate constant associated with it. And this one is considered fast. So this slow one, we call this the rate limiting step. And it determines the rate law. Okay, so these two reactions combine to give us our overall reaction, H2 plus 2ICl goes to I2 plus 2HCl. So looking at our overall reaction, we can't determine our rate. We have to look at our slow elementary step. So according to our slow elementary step, our rate would be equal to H2 ICl, or K, there's a K in there, K times H2 ICl, and you're just going to use K as a generic K in this case, because we have our first step being the slow step. And we can see that that does not have the same molecularity as our overall reaction. It has the molecularity of our slow step. So it is bimolecular, not termolecular, as our overall would indicate it would be. Now, in this case, we have our slow step being our first step. What happens if we have a slow step in the middle? Something like this. So we have 2NO gas. This might look familiar. Going in that direction is K1. Going in this direction is K2. And this is our fast step. And then we have N2O2 gas plus O2 gas. And then here's our K3, giving us 2NO2 gas. And it's our slow step. Overall, we get a reaction of 2NO gas plus O2 gas goes to 2NO2 gas. Our second step is our rate limiting step, so that's what our rate will be based on. However, if we were to write it just like it's written here, it would say rate is equal to our K times by N2O2 times by O2, right? So the stuff that's in that reaction. However, if we look, this is an intermediate, and intermediates cannot be part of a rate law. Very, very important. So this needs to be rewritten in terms of just reactants, and like I said, I will do this in a separate video, but what you would actually get, you would get rate is equal to K and O squared O2. And I'll show that in a different video, how we get to that. Okay. So I want to do all that. Okay. Last thing I want to talk about very quickly is catalysts. So catalysts, that's the last thing we can do to speed up a reaction. They speed up reactions by lowering our activation energy. So they speed up reactions by lowering the activation energy. Okay, so they do not participate in the overall reaction. So they're not part of the overall reaction when we add them up together. So they don't get consumed. So if you have a species that is consumed, it cannot be a catalyst. So anything within the reaction itself is not considered a catalyst. And it lowers our activation energy by giving our reaction an alternate path to take. So it changes the reaction mechanism. So for instance, if we have a reaction, we have our reactants, our products, and our activation energy looks like this. Right? If we have a catalyst, it would look like this instead. So it would still have the same reactant and product energy, but then it would go something like this. So we would lower activation energy by taking a different path. Our catalysts can be homogeneous or heterogeneous. So homogeneous, that's when our catalyst is in the same phase. Physical state. As the reaction. And then our heterogeneous is a different state. So our reactants. Okay. One special kind of catalyst is called an enzyme. An enzyme is a biological catalyst. And it is a protein molecule. So a huge macromolecule within the body, or within any living organism. Its structure allows it to have what's called specificity. So it catalyzes one reaction type, one specific reaction, or one molecule type. So it's specific to a specific molecule, a specific molecule type, so an amine or amide, specific bond type, an amine bond, or a specific stereoisomer. Okay, that is all.